Hello, here are solutions to the problems assigned out of section 7.4. So the first one, we're supposed to establish this trigonometric identity. Okay, in my lab it gives you very explicit steps to work through, and we're just going to do it freestyle. So the way we're supposed to do this is typically begin with one side of the expression and try to turn it into the other one using things that we know are true. And typically, one side will be simpler and one side will be more complicated. So for example, in this one, the left side, tan of theta plus cotan of theta all times sine of theta, there seems to be more going on than the other side, which is just secant theta. And I generally recommend begin with the complicated side and try to simplify it towards the other one. You could begin with either side and work towards the other, but it's generally a lot harder to take a simple thing and turn it complicated than the other way around. So we're going to begin with one side of the expression, tan of theta plus cotan of theta times the sine of theta. And we're going to do a bunch of allowable steps, and at the end we should have just a secant of theta. I typically like to approach these problems by always talking of things in terms of just sine and cosine. So tan of theta is sine of theta over cos of theta, and cotan of theta is the reciprocal of that, cos of theta over sine of theta. This would then all be times the sine of theta. Okay, similarly, at the end we want to get a secant theta, but that's going to be the same thing as 1 over cos of theta. So maybe if I can just get to 1 over cos of theta, I'll know that I can then transform that into secant of theta. Okay, so back up at the top, we've got these two ratios times the sine of theta, and honestly the most immediate thing that I see to do is just distribute the sine of theta to both of these terms. So we end up with sine of theta over cos of theta times sine of theta plus cos of theta over sine of theta times sine of theta, which simplifies as sine squared of theta over cos of theta plus cosine of theta. Okay. So then what can we do with this? Well, observe that the second term, cosine theta, doesn't have a denominator. In other words, its denominator is 1. If I wanted to add these two fractions together, I'd have to give them a common denominator. And the common denominator would just be cos of theta. Now the first term already has cos of theta as its denominator. So if I wanted to give this cosine of theta a denominator of cos of theta, I have to multiply and divide by cos of theta. When I distribute that out on that second term, we now have sine squared theta over cos theta, that's our first term, plus cos squared theta over cos theta. And if I combine both of these into a single fraction, we get sine squared theta plus cos squared theta all over cosine of theta. And what is sine squared of theta plus cos squared of theta equal to? 1. So from the beginning, we can now read through our argument in the following progression. So the tangent of theta is just sine of theta over cos of theta. The cotan of theta is just cos of theta over sine of theta. So there's no argument here. This is definitely equal. All we did is replace tangent with sine over cosine, and similarly for cotangent. Why is this equal to the next line? Well, all we've done is distribute sine of theta times the first term plus sine of theta times the second. And here they are. So there's no argument. Okay, this line is definitely equal to this one. It's just the distributive property. How do I get from here to here? Well, sine of theta times sine of theta is what we notate as sine squared of theta. And here I've just canceled sine of theta over sine of theta to leave behind just a cosine. Again, no argument, just simple arithmetic. Okay, well now I just want to give these common denominators. So I take the second term, which was just cosine theta, and I multiply it by 1. Specifically, I multiply it by cosine theta over cosine theta. And since multiplying by 1 doesn't change the value of anything, well, hooray, this is definitely equal to that. This second term of cos theta times cos theta over cos theta, I can now just simplify as cos squared theta over cos theta. No argument that these two things are equal. Now that I have two fractions with the same denominator, I can collect their sum into one term. And sine squared theta plus cos squared theta is equal to 1. That's the Pythagorean identity, and I still have that denominator of cosine theta, and 1 over cosine theta is secant theta. So at every step, it's certain that one thing is equal to the one that came before it. So since this tan theta plus cotan theta times sine theta is definitely equal to this, is equal to that, to that, to that, to that, to that, to that, to this, we can conclude that indeed, for all angles theta, the tangent of theta plus the cotangent of theta times the sine of theta is simply equal to the secant of theta. And that's how these are all going to progress. We're going to begin with a more complicated side, perform a sequence of single, clear steps, and at the end we'll have transformed it into something that looks totally different. So, certainly the left side looks more complicated than the right, so I'm going to start with cosecant of theta plus cotangent of theta times cosecant of theta minus cotangent of theta. And what do I know will be at the very end of everything? Hopefully just a 1. I want to show that this is just equal to 1. And so let's just phrase everything in terms of sines and cosines. So cosecant is 1 over sine theta. Cotangent is cosine theta over sine theta. Times cosecant is 1 over sine theta minus cotangent, that's cosine theta over sine theta. Okay, well now I've got inside the parentheses 2 fractions that already have common denominators, so I'm just going to do that. So this is 1 plus cos theta over sine theta, and here I have 1 minus cos theta over sine theta. Now I've got 2 fractions that I'm multiplying together, so I can make this one fraction of 1 plus cosine theta times 1 minus cos theta, and the denominator is just sine squared theta. And finally, look at that numerator. It's 1 plus cos theta times 1 minus cos theta. Now remember your difference of 2 squares factoring. A squared minus b squared factors as a plus b, a minus b. So here we have 1 plus cos theta, 1 minus cos theta. In other words, something plus something times the first minus the second. First plus second, first minus second. So while you could distribute that whole thing out, it is just going to be a difference of 2 squares. And switching back to red, it's just going to be 1 minus cos squared theta over sine squared theta. Okay. Now also remember your trigonometric identity, sine squared theta plus cos squared theta equals 1. So if I subtract cos squared theta from both sides, we get sine squared theta equals 1 minus cos squared theta. So in the numerator up here, instead of 1 minus cos squared theta, this is sine squared theta. And the denominator was already sine squared theta. And what's something divided by itself? It's 1. So once again, okay, we just replace everything in terms of sines and cosines, and then we start doing arithmetic. And we have to make use of some trigonometric identities that we've used before, like the basic Pythagorean identity. Now this time we didn't do sine squared theta plus cos squared theta equals 1, we simply moved it around a little bit to say that 1 minus cos squared theta can be replaced with sine squared theta, and now I cancel these out and we just have a 1 left behind. So now, I've said start with the complicated side and make it look like the simple side. Both of these look more or less of the same ugliness. The right has a fraction in it, but the left has cotangents and cosecants, so I'm going to start with the left. Now this definitely can be replaced with cosine theta over sine theta, I'm sorry, the angle here is a u. Cosine u over sine u, minus 1 over sine u. Okay, well now I've got a common denominator already. So this is going to be the cosine of u minus 1 over the sine of u. Okay. Now what we want is a denominator of 1 plus cos u. So if we happen to know at the very end we're looking to get a denominator of 1 plus cosine u, I can introduce that denominator by multiplying this by 1. Now, what form of 1 do I want to multiply by? I'm going to multiply by 1 plus cos u over 1 plus cos u. This way, I'm only multiplying by 1. I am not changing the value. Why am I multiplying by this? Because I already know that I want a 1 plus cos u in the denominator, and now I'm going to get it. But we do have to also multiply the numerator by that, and then we'll just see what happens. Okay, so the top is again a difference of two squares. Okay, it's cos u plus 1, cos u minus 1. So that's going to multiply out as cos squared u minus 1. And our denominator is sine u times 1 plus cosine of u. Now we could distribute this out, but there's a reason I'm not going to. So we already know that our desired denominator is 1 plus cos u. So that's already there. It happens to be in parentheses, but because I know I want a denominator of 1 plus cos u, I want to cancel this off somehow. I don't want to distribute it and then have to refactor it out later. Okay. So now, just like last time we did sine squared u is 1 minus cos squared u, and up in the top I'll put in blue, remember this came from a Pythagorean identity, sine squared u plus cos squared u equals 1, which means if I subtract 1 from both sides and subtract sine squared u from both sides, we get cos squared u minus 1 is negative sine squared u. So that's what we're going to do in that numerator. So cos squared u minus 1 I replace with negative sine squared u. My denominator is the sine of u times 1 plus cos u. And observe I have sine squared in the numerator and sine u in the denominator. If I cancel out sine u over sine u, we're left with negative sine u. I still have 1 power of sine in the numerator, and I've canceled it off the denominator, leaving behind just 1 plus cosine u, which was exactly what we wanted to get. So the little trick that was introduced in this one is that you had to do something a bit counterintuitive. You had to multiply by 1 plus cos u over 1 plus cos u. I shouldn't say had to. This was simply how I saw to do it, but I'm sure there are many other ways to get from the start to the finish. For me, since I saw that we wanted to introduce this denominator of 1 plus cosine u, at a certain point I just had to make it appear. But I can't just multiply the denominator by 1 plus cos u unless I also multiply the numerator by 1 plus cos u. Alright, now I think one side is clearly more complicated than the other, so we'll start with 1 minus the quantity cosine squared theta over 1 plus sine theta. Okay, and at the end of the day, hopefully I can make this look just like a sine of theta. Well, I've got two fractions, let's give them a common denominator. So there's a 1. Okay, well, now I can combine these into a 1 plus sine theta minus cos squared theta over 1 plus sine theta. All right, I'm going to do a similar substitution. Use a Pythagorean identity to replace my cos squared with 1 minus sine squared theta over 1 plus sine theta. And again, this just comes from sine squared theta plus cos squared theta equals 1. Okay, now if I subtract sine squared theta to the other side, we get cos squared theta equals 1 minus sine squared theta. So it's a similar manipulation that we've done before. I'm just taking this rearrangement of the Pythagorean identity and plugging it in for this cosine. So instead of a cos squared here, we call it 1 minus sine squared. Now I need to distribute that negative sign, and we end up with 1 plus sine theta minus 1 plus sine squared theta over 1 plus sine theta. Observe that the 1 and minus 1 will cancel each other out, leaving behind sine theta plus sine squared theta over 1 plus sine theta. That numerator, I can factor a sine theta out, leaving behind 1 plus sine theta. I still have a 1 plus sine theta in the denominator. And now I can cancel that out with its counterpart in the numerator, leaving behind just sine theta, which was exactly what we wanted to have at the end. So again, just do some arithmetic. I see two different things being added or subtracted, so let's give them a common denominator. I have a mixture at this point of sines and cosines, but I know I'm looking for just a sine at the end. So somehow this cos squared is going to have to interact with these signs over here, or the ones in the denominator. So I use a Pythagorean identity to replace cos squared with 1 minus sine squared, and at this point the 1's cancel, and now I have a bunch of sines. Factoring 1 out of the numerator allows me to do exactly the cancellation that leaves me behind the sine theta that I wanted at the end. All right, 1 minus cos theta over 1 plus cos theta equals sec theta minus 1 over secant theta plus 1. I happen to think the right-hand side looks more complicated. This is probably not how MyLab expects you to do it. They probably default to make the left look like the right, but equality signs are symmetric, so if I can make the right-hand side look like the left, it's just as good. And I like to take the more complicated side and make it look like the simpler side. Algebraically, these two things look pretty similar, but secants are less pleasant to me than cosines. So the first thing I'm going to do is convert secants to 1 over cosine. Now true, we now have fractions within fractions, but we can deal with that. So this overall numerator, I'm going to give a common denominator of cosine theta. Okay, and this one as well. All right, now I can simplify that numerator as 1 minus cosine theta over cosine theta over 1 plus cosine theta over cosine theta. And now if I just multiply by cos theta over cos theta, in other words, I multiply by 1, this cosine theta cancels that one, this cosine theta cancels that one, and I'm left behind with 1 minus cos theta over 1 plus cos theta. And that's really all there is to it. Now that we've gotten to the end, and this is a fairly common thing in math, we've managed to do a perfectly correct solution. There is nothing wrong with this. But I notice at this point that all I really had to do was multiply by cosine over cosine. This work here was a little unnecessary. And we should always be willing to go back and fix up our old work, even if it was correct. If we can make it a little bit simpler, it will be easier for someone else to follow. So I'm going to come all the way back to the end here, to the beginning, I'm sorry, and say, you know what? The only work I really did here was multiplying by cosine theta over cosine theta. So let's come back to the beginning and multiply by cos theta over cos theta. I'm multiplying by 1. This doesn't change the value. So now I get cosine theta secant theta minus cosine theta over cosine theta secant theta plus cosine theta. And we happen to know that since secant theta is 1 over cosine theta, if I multiply secant theta by cosine, or you could even look at this as cross-multiplying here, cosine theta secant theta is just always equal to 1. So this gives me 1 minus cosine theta over 1 plus cosine theta, which is what we wanted to change this into. And we don't have fractions within fractions, which might look a little bit nicer. So you should always be willing to make your work better than it was before, even if the old version was correct. Okay, moving on. Well, this time I think the left-hand side is clearly the uglier side, so we'll start with that. The negative tangent of t plus cosine of t over 1 minus sine of t. I'm going to replace everything in terms of sines and cosines, so this is negative sine t over cos t plus cos t over 1 minus sine t. So I want to give this a common denominator, but the two denominators are just completely different, so the only common denominator I can come up with is the product of the two. So this first term of sine t over cos t, I'm going to multiply by 1 minus sine t over 1 minus sine t. In other words, I'm multiplying it by 1. The second term of cosine t over 1 minus sine t, I'm going to multiply by cos t over cos t. In other words, I'm multiplying it by 1. But now, both terms will have the same denominator. So the first term has denominator cosine t times 1 minus sine t, and so does the second. Let's take care of their numerators, though. The first term, by which I mean this bit here, is going to be a negative sine t times all this, and the second term is just going to be a straightforward cos squared. So, distributing a negative sine t in that first numerator, we get negative sine t plus sine squared t, and here I have a cos squared t. Now that both terms have the same denominator, I can just combine them into negative sine t plus sine squared t plus cos squared t all over cosine of t times 1 minus sine t. Observe that I now have a sine squared t plus cos squared t in the numerator. That's just a 1. So I've just replaced my sine squared t plus cos squared t with a 1. Now this 1 minus sine t over 1 minus sine t can be cancelled out, leaving behind 1 over cosine t, aka secant of t, which was exactly where we wanted it to finish up. So again, each step clearly follows from the one before it and is definitely equal, and therefore overall the two sides are definitely equal. All right. I think there's no argument which side looks worse, so let's just start with that and get to it. So I'm going to start with negative cosecant v minus cotangent v squared minus 1 all over the secant of v times the cotangent of v minus the cosecant of v. And I'm hoping at the end of the day I can make this look like 2 times the cotangent of v. Well, I'm going to change everything into sines and cosines. Okay, so negative, parenthesis, cosecant is 1 over sine v. Cotangent is cosine v over sine v. That's all still got to be squared, minus 1, all over 1 over the cosine of v times, parenthesis, cosine v over sine v minus 1 over sine v. Okay. I'm just going to observe that inside the parenthesis, both terms already have a common denominator, so I'm going to go ahead and do that. So this is 1 minus the cosine of v over sine of v squared, minus 1, and the one on the bottom, in the denominator, becomes cosine v minus 1 over sine v. A lot of people at this point would be tempted to do the following cancellation, say cancel one of these with that, but you can't do it because this parenthetical term has not been factored out of the numerator because of this minus 1 hanging on here. So I can't just cancel one of these with those, if that's what you were thinking of doing. Okay, well now I'm just going to square that numerator. Okay, so the denominator, when I square it, is just sine squared v. The numerator, when I FOIL out a 1 minus cosine v, is going to be 1 minus 2 times the cosine of v plus cos squared of v. And I see a little typo I made, so I'll quickly fix that. My denominator, if I multiply everything out, becomes cosine v minus 1 over cosine v sine v. Okay. So there are a couple of things I could do at this point. I'm going to look at my overall numerator, in other words, all of this, and give it a common denominator. This term has denominator sine squared, so I'm going to give this a denominator sine squared. In the interest of saving space, I'm just going to mark it like that, and instead of calling this 1, I'm going to call it sine squared v over sine squared v. Because now they both have the same denominator, so I can collect this as, let me just distribute this negative sign out as well, so I get a minus 1 plus 2 cosine of v minus cosine squared of v minus sine squared of v, that's this minus sine squared of v, all over sine squared v. All of that is still over cosine of v minus 1 over cosine v sine v. All right, now a couple of things. Negative cosine squared minus sine squared is just cos squared plus sine squared with a minus sign distributed across the whole thing. So this is all equal to minus 1. Okay, so I'm going to start erasing this top line. Okay? Just remember, we've done legit steps the whole way. It's just this is a fairly involved problem and I can't quite fit it on one page of work. So, continuing. If I replace that negative cos squared minus sine squared with a minus 1, my numerator looks a little simpler now. We can call this 2 cosine of v, that's this term right here, the 2 cosine of v, minus 1 is just minus 2, over sine squared v all over cosine v minus 1 over cos v sine v. So it's starting to look a little better. One thing I can do is resolve now the fact that I have one fraction over another fraction. Okay, so this can be called 2 cos v minus 2 over sine squared v times cos v sine v over cos v minus 1. All I've really done at this point is said division by one fraction is multiplication by its reciprocal. And now we have some nice things that happen. For example, I can factor a 2 out of the 2 cos v minus 2, leaving behind this. And now there's some cancellation that happens. Everything is fully factored. I can cancel this cos v minus 1 with this one. I can cancel this sine with 1 power of sine there. So what do we have? Let me just erase a little bit more space. We've got a 2 cosine v over sine v, and what is cosine v over sine v if not cotangent v, which is what we wanted to get at the end. Okay, so this was a bit long, and it did rely on a lot of arithmetic, but it's the same basic stuff. Okay, work with sines and cosines, do common things like finding common denominators, using trigonometric identities like sine squared plus cos squared equals 1. In this case, it was a negative cos squared v minus sine squared v equals minus 1. And just hack through it. I mean, if your algebra skills are up to snuff, then you can do these things.